Hi, everybody. Today we are going to talk about the element of color. And let me get to the slides. So let's talk about color. And we've looked at line, value, shape, mass, space, and texture. And now we're looking at color. So here's an introduction to color. And here's that painting I wanted you guys to write down from last lecture. Paolo Veronese, The Wedding Party at Cana, oil on canvas, 1563 in the Louvre. This is a crazy large painting, like 12 feet high and 15 feet wide. I think this might be the best painting ever. A lot of people like the Mona Lisa, but I don't actually think that's this great of a painting. This painting is awesome. And I wanted to point out that whenever you're labeling artwork, there's a specific format. First, you list the name, so the artist, then you list the title, then you list the medium, so oil on canvas, then you list the date, and then you list its location or its collection if that's available. So color affects our lives. It's physical, so it's made up of photons. It's perceptual, we see it. Communicates information. It's emotional, it affects our feelings. It functions like language. And here is a basic color wheel. You can see the relationship of all the colors and how they're mapped out. And so you may know that Sir Isaac Newton discovered or maybe mapped out scientifically that bands of color make up the visible spectrum. Discovered is a word that's often used when describing this, but other people noticed what a prism did. It's just he divided up a prism into specific colors. And so you've got the red, orange, yellow, green, blue, and violet. Can you think of a naturally occurring spectrum? Hopefully you can, a rainbow. And so that color wheel is based on 12 pure hues. It's a 20th century version of the circle concept first developed by Newton. He found that both ends of the spectrum could be combined into the red-violet hue. So what he discovered is that at the infrared edge of the hue, we saw a red, and then all the way up to ultraviolet, we're seeing a type of red or an ultra red violet. And so because of that, you can wrap all of the colors into a circle to understand it, and again, to understand the relationships between the colors. See how that wraps around, red to red? So let's look at some historical color wheels, and you can see that people have been trying to conceptualize color circles or color relationships for a long time. Particularly the one up on the upper right is quite interesting. And you see the different colors mapped out in Latin and how they might relate to each other. So all these interesting geometric relationships were proposed. You see down with Harris in the bottom left-hand corner, we're much closer to the contemporary color wheel. Hader is especially important. Um, he gave names to red, yellow, and blue. Those primary colors, he called them primordial, which is funny. Here's his wheel invention, sort of a wheel. And this shows the mixing we would see. So upper right, you've got red. Upper left, you got yellow. And where they come together, you've got orange. And so you can follow that along throughout this whole mapping and see what the different color combinations produce. Look at that sower bee. It's quite beautiful. We're at rung, and rung is interesting because it actually maps out a color globe, so a real color space. Um, the concept is that color can be described as a three-dimensional object, not just as a two-dimensional flat surface color wheel. We'll see a few of those in a minute. Here we go. This is Rung's color globe. And you can see around the equator are the pure hues. Up at the top is white, and then we've got these tints to the pure hue coming down toward the equator. And then on the bottom, you've got black, and so we've got shades down to black. So you can imagine this as a ball, essentially. Here's a bunch more historical wheels. Much more contemporary. Chevreul is particularly interesting. A really important theorist, a chemist in the 1800s in France who figured out a lot of things that happen with color when our eyes see one color and the after effects. So if you look at something that is red, for example, and then quickly look away at a white wall, you will actually see a green after image. And you guys may have seen optical illusions that work on this principle. Really beautiful wheel. Ostwald is worth noting. We'll see some slides of his work. And Itten. Itten was a really important theorist when it came to color harmony. And you can see the bottom right, his version of a colored globe, so three-dimensional space, can be cut out of paper. So you can imagine if you can cut this star shape out of paper, you could then conceivably fold that into a globe. Here's Itten's color wheel showing the relationship of colors and their mixtures. All kinds of color wheels. So color spaces or systems are different ways of understanding how color exists and interrelates. Color systems present a visual mapping of color and space. So these that we'll see are all evolutions of Rung. Let us look at a few. So Newton, Munsell, Ostwald, Lab, Itten, Albers, CMYK. So let's look at a few of these. Ostwald, who I mentioned, was also a chemist, but his three basic colors were yellow, red, blue, and green, whereas we think of the primary colors, or those primordial colors, as just yellow, red, and blue. But he was working on color harmony as well. And we'll see his contemporary Munsell in a moment. Um, but it uses these components of color, which is hue, chroma, and value. So it's an idealization of the overall organization of color. Here's his wheel. And this is a cross section of his globe. So you can imagine these stacked on one another and expanded. We see right in the middle a grayscale going from black up to white, and then tints on the top going from white to the full hue, shades on the bottom going from black to the full hue, and then everything in between, which we call tones, which is gray going toward the full hue. Here's another description of that. Here's a cleaned up version. Here's a section of that. We can see the yellowish orange opposing the blue. You see on the upper right, something like this is extremely rare, this full-on painted color globe. I would love to get one of these. They're just awesome objects. Think how much work this would be to make one. On the cell, a color space that specifies colors based on the three color dimensions. We just saw this happening, hue, value, and chroma. I'll expand upon that in a moment. Actually, the system is used in forensics and soil research now. Um, it gives colors in numbers. So it's not particularly great for the artist, but it's great for the scientist because they could say red number 5 at brightness 2 um, at intensity 4. So here's what I'm talking about. Brightness up at the top, intensity, that's pureness, out at blue number 12, and then color, blue number 12, for example. So each of the positions around the color wheel will be given different names, like red number 5. That just tells you the positioning around the wheel. Intensity, so the further out on that wedge is how pure that color is. And then up the middle, again, would be its brightness. And I'll just mention hue, chroma, and value again. Hue is like the parent color, like I could say red. Chroma is how strong that red is. And then value is how bright that red is. We use those three determinants to specifically identify a color. Something to mention, and I've been using these technical terms, they are actually technical terms, is tint, tone, and shade. Whenever you add white to a color, it's a tint. Whenever you add gray to a color, it's a tone. Whenever you add black to a color, it's a shade. So those are technical terms that have real meaning. If I say something like a different shade of orange, I'm still talking about a specific orange. I'm just talking about one with more black added. So they're specific terms and you should use them correctly. This is what Munsell's space maps out to. So not as idealized as the other globes we've seen, but fits with his ideas perfectly. And you can see here, he postulates that red can hold the highest intensity of all the colors, while sort of blue-green up in the upper left can hold less intensity of color. So intensity is not brightness. It's sort of spikiness or chromaticity. So he didn't want to rely on names that are subjective. He wanted to rely on something more objective, numbers. He has a different number of primaries. So like I've said before, those three major primaries are red, yellow, and blue. He has 5 principal hues: red, yellow, green, blue, and purple. Intermediate hues. So our usual many intermediate hues would be something like orange, green, and purple. That would be mixtures of the primaries. Here he has them identified as primaries and primaries themselves or intermediates. And here's what I mentioned when we were looking at Munsell um, and and how value works. We already talked about value when we looked at value as an element, um, but this just maps out what the slide we looked at a few minutes ago says about value and that central core of going from black up to white. Chroma, a color's saturation or brilliance. So we would say probably a blue that has been shaded, so it's had black added would have less intensity than a pure blue. This just mentioned a no box, and this is what a couple of the tubes I call in color theory class are labeled as. Um, because we don't use them till later in the quarter. But CMYK are printing colors. They rely on transparency for combination. C is cyan, M is magenta, Y is yellow, and black is K for some reason. Maybe not to be confused with B for blue. Here are all the colors mapped out and their different available intensities for the Munsell color system. Now, lab is a digital space. So this is how we're seeing things on our screens. And what's particularly interesting is that the available digital space for showing color is less than our visible spectrum. So even with our phones today, we still can't see reproduction of color that we would see with our eyes. It's quite inadequate, actually. Interesting thing to note is black body radiation. So that would be a theoretical pure material. So something like pure iron will glow determined by its temperature. And so our sun is at about 5,000 degrees Kelvin. So right in there between 400 and 600. And that, important to note, that's different than the reflected color of the surface of an object. So this is like staring at the sun. I would actually say we're somewhere around right at 4,000. You can see by the color. So that lab space is used to convert one color, like RGB, on a monitor to another color space, like CMYK, on a printer. It's how the two color spaces talk to one another. So RGB means red, green, and blue. So those are additive primaries. You see, 4 slideshows and 3 mistakes on slides already. And HSB is hue, saturation, and brightness. So this is more common to the way we're understanding things with chroma and hue and value. So I think that this color space makes a really beautiful mapping. This is from above. This is from the side, and this is from above. Really cool. So the reason it's called lab is because your measurements here are in luminance, the red-green location, and that's opposed by the blue and yellow location. And from that, you can map out things using numbers, sort of in the way that Munsell space used numbers. But this is a digital version. Itten, Bauhaus educator, conceptualized color as a star, as we saw, based on the color wheel. Most of his work was from the 1920s. This is that star again. Here's his globe when you sort of fold that star into a globe. He was really trying to find universal and harmonious combinations of color. Really interested in psychology and metaphysics, um, and even thought that certain philosophies fit with certain colors. And that's along with the combinations that those might make. So his notion was that red naturally fits with a square, and orange naturally fits with a triangle or a rhombus, and yellow naturally fits with a triangle. So you can see that red combined with yellow equals this intermediary shape. Yellow combined with blue makes this sort of bulbous triangle. Blue with violet and red down at the bottom. So blue being a circle, red being a square, we get an oval for violet. Again, these are just theoretical. And at the Bauhaus, another professor named Kandinsky, another famous painter, sought to find the association colors have with shape. It's not scientific, but is really the basis of Witten's theories. So they passed this out to painting students and told them to paint the proper color into each of these shapes. And most of the students painted them like this, just like we saw on the last slide. Now, a caveat here is that they had also been taught by Itten, so they've already been under the influence of his ideas. Nonetheless, it appears that most of them agreed with these color and shape combinations. So here's some of that philosophy. So yellow being bright knowledge, and violet being dark emotional piety, blue being submissive faith, and orange being proud self-respect, red and green, so material force with sympathy. You can hear some of the interpretations. Um, Red plus yellow would be power plus knowledge equaling self-respect. So there's a lot of built-in Western European and Christian thought here, but nonetheless, it's interesting in that he was trying to find universal meanings for colors. So here's a couple of those. Up on the top left is Newton's. Then we've got the color star. Then we've got the student's contemporary color wheel that we use in color theory class. Down at the bottom, we've got a smooth gradiated globe. Then we've got Ostwald. Then we've got Chevreul. This is the color wheel that I made. It's 24 steps. So you can make definite combinations, but it's not so gradated. So you can still see individual steps, but expanded upon the 12 basic hues. This is a color wheel I painted based off of that. And you can see it goes in pretty smooth steps around the whole wheel. So color has the attributes, three components: hue, value, saturation. Saturation is used interchangeably with chroma. And I'm just reiterating this again. Hue is the name of the color. And again, think of this as the parent color. Value is how bright that color is. And there are built-in values to colors, like a blue is never going to be as bright as a red or a yellow. So you guys know that. If we are just looking for a brighter color, we want to use yellow. If we're just looking for a darker color, we would use blue or violet. And then chroma. So I just want you to see up at the top, is a painting with high chroma, like boosted above its natural level of chroma so you can see, and then one with the saturation taken out. And I want you to notice that they are the same values, so same amounts of brightness. They are the same colors in terms of which colors are used. It's just that the one on the right has less chroma, it has less saturation. So, how we see color, our eyes have about 6.5 million cones. They're sensitive to red, blue, and green light, which are called additive complements. They take in and sort out various stimuli, color sensations, which are sent to the brain. On the other hand, we've got more rods. We've got 100 million of those, and they take in and sort out darks and lights. So both are photoreceptors that make up the retina of the eye. So the rods determine brightness, and the cones determine color. I want you guys to watch this video. It's very interesting when you go back through this lecture slides, the PDF. This is a wacky use of color from Instagram. This is an interesting slide. So there's a lot of studies, and most color theory outside the art realm is anthropological. This is naming distribution. So what's going on here is the breadth of color that people will ascribe a specific name to. So this is saying that there is a wider range of colors that people will just say are green than yellow, and yellow has a small percent of colors that people would name as yellows. Um, Red is much more specific. You can see left bottom and right bottom. Um, People have in mind what a specific red is. They do have more pink. So more people will identify more pinks than they will reds. So how we're seeing color. So the object color, or what we would call the local color, that appears to our eyes is determined by the wavelengths of light reflected. So a red cushion illuminated by white light appears red because it reflects mostly red light and absorbs the rest of the spectrum. So if I shine a light down on red fabric and everything else bounces off that except red, we're seeing a red cushion. Everything's absorbed except red. So what's bouncing back to our eyes is red. Arrow. When all the wavelengths of light are absorbed by a surface, the object appears black. When everything's bounced back to our eyes, it appears white. Black base, white feathers. And we most often say that black and white are not truly colors. They're called achromatic or without colors. And that is because they're either all reflected or all absorbed. But we actually hardly ever see white light surfaces in pure black. So you would have to be in a cave to see pure black. Um, you would have to be in a white cube with equal white lighting to see white. Otherwise, we're almost always seeing some ambient effect of other colors on those surfaces. It especially happens with white. Um, there are so many different varieties of what we think of as white. When we look at a white wall, or what we just think of as a white wall, and then we compare it to a sheet of paper, we can see how different those two whites really are. So there's a huge perceived variety of whites that we might label as white. We know about value. We know about tint, shade, and tone. Again, tint adds white, shade adds black, tone adds gray. I think I'll stop there at the types of color. Okay, tune in next time for more about color.